All right, we got a long question in terms of conceptual input, but a pretty easy result, and it's pretty fascinating, to be honest. The statement reads, consider a plane loop of wire that carries a steady current I. We want to calculate the magnetic field at a point in the plane. We might as well take that point to be the origin. It could be inside or outside the loop. The shape of the wire is given in polar coordinates by a specified function r of theta. Show that the magnitude of the field is B equal mu naught I over 4 pi closed integral d theta over r. B. Test this formula by calculating the field at the center of a circular loop. C. The lattice spiral, I don't know if I'm pronouncing it right, is defined by r of theta equal a over square root theta from 0 to 2 pi for some constant a. Sketch this figure and complete the loop with a straight segment along the x-axis. What is the magnetic field at the origin? D. For a conic section with the focus at the origin, r theta equal p over 1 plus e cosine theta, where p is the semilattice rectum, the y-intercept, and e is the eccentricity, which you might remember better from mechanics, where for e equals 0, we get a circle, okay? And for e between 0 and 1, we get an ellipse, and for e greater than 1, we get a parabola. Again, we use that for defining orbits. Show that the field is B equal mu naught I over 2p, regardless of eccentricity. All right, well, let's just calculate away. This all came from a paper that he sourced in the book, which if you do want the link to the paper, I can include it, or to send me a message. So for A, we see that dl cross r hat is equal to the magnitude dl sine phi in the z hat direction, and that reduces down to negative r d theta z hat. Okay, so we substitute that in. Pretty quick, pretty easy. And then we end up with the integral form that we wanted. Good to go there. Note that because we're at the origin, script r goes to regular r. No big deal there. For a circular loop where little r equals big R, which is a constant, we plugged it in. It gets carried outside the integral, and you get a 0 to 2 pi integral, which is pretty easy. 2 pi's cancel, leaving you with mu naught I over 2r. Looks familiar. Good to go. The graph we'll include at the end, but the calculation is the same. Just plug a over square root a into the denominator. You know, anytime you're dividing by a fraction, you multiply by the reciprocal. Go ahead and do that, and then you're left with the basic power rule. And then you end up with mu naught I square root 2 pi over 3a. Good to go. And then the conic section, again, divide by a fraction, multiply by the reciprocal. We end up with this integral of 1 plus e cosine theta d theta. Again, since cosine is 2 pi periodic, that cancels out. So we're just left with a factor of 2 pi from the factor of 1 that gets integrated to theta. And so the 2 pi and the 4 pi cancel to a 2, leaving us with mu naught I over 2p. Again, to show that it is regardless of eccentricity. And then we have a nice little graph here where we see that r of theta spirals into what looks like a stability point or curvilinear trajectory. So pretty cool. Nice to see that.